Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, you know that thermal management in PCs is very important. Actually, computer cooling is required to remove the waste heat produced by computer components to keep components within permissible operating temperature limits. Computer fans are widely used along with heatsink fans to reduce temperature by actively exhausting hot air. Now, with the invent of these 7 nanometer chips, the thermal management has been a little bit easier or better. But when we are talking about high gaming PCs or laptops, when we are talking about multitasking abilities or even high FPS, in that case, thermal management to be taken care of very seriously. Because in high gaming laptops with high setting gaming, the temperature may rise up to 80-90 degrees centigrade. In that case, we need to be very serious about thermal management system. Now, if we are talking about thermal management system, we should think what type of cooling is required, whether it is liquid cooling or air cooling. Again, for considering this thermal management, we should talk about the thermal paste also, whether it will be silicon based paste or carbon based paste. That is also very important. Generally, you have to follow the air cooling system. Fan is also there, but that is not sufficient enough. In that case, we are using heat pipes, right? So what are the heat pipes? You already know heat pipes are actually made up of coppers, and inside that one little bit of liquid is provided. Actually, while considering thermal management, we should know that huge amount of heat is produced on the different parts of the computer or PC. From the chip itself, huge amount of heat is being liberated, and that heat to be transferred through the outdoors with a very faster rate. In that case, we need a material which is having high thermal conductivity. In that case, we should use heat pipes. At the hot interface of heat pipe, a liquid in contact with thermally conductive solid surface turns into vapor by absorbing heat from the surface. The vapor then travels along the heat pipe to the cold interface and condenses back into a liquid, releasing the latent heat. So in this way, heat is transferred very quickly. Today in our video, we'll show laptop cooling using heat pipe. So we have arranged the different components as per our convenience. It will not be arranged in this manner. As per availability of space and optimization, the components are arranged inside this laptop in a different way. Our aim is to show the basic method of cooling using heat pipe. What we have done is we have provided the chip here. This is made up of silicon, and this is the heat pipe which is connected with the top surface of the chip. And here this space we can see this is fins to have a better heat transfer, and from the top we have provided fan. Down this face we have provided some slots, which is rectangular slots for transferring air from the bottom surface, right? And in the heat pipe we have provided 3 different spaces. First space from here to here, this is known as evaporative zone. Second space from this location to that location is known as adiabatic zone, and the third part, the last part from here to here, this is known as condenser zone. So heat will be transferred from here to here with a high specific rate compared to the normal copper tube. Its effective thermal conductivity is at least 10 to 10,000 times depending on the length of the copper tubes. For starting this simulation, you have to depend on flow simulation environment. That will be started with flow simulation and wizard itself. Let us consider the name of the project as project 3. Next to that, to select that unit system, we can select unit system as per our requirement, but better to select the SI unit as the standard one. Next to that, we can select pressure in the form of bar and temperature will be in degrees centigrade. Next to that, it will be an internal analysis. Together with that, you have to select heat conduction in solids, and other things are not that much important in this case. Next to that, we will select the default fluid as air, and together with that, for heat pipe we have to select water as a liquid. So those things will be in different subdomains, so we need not consider about free surface technique because those different fluids will be in different subdomains. we're considering water as the liquid for heat pipe. Next to that, we have to select the material. Let us take material to be made up of aluminum, that is aluminum 6061 as the default material, and the copper tubes will be provided later on while applying boundary conditions. In this case, we can consider the outer walls will be also having some kind of convection with a specific convective heat transfer rate. Let's provide the convective heat transfer rate of the outer walls as 40 watt per meter square degree Kelvin at a temperature of 20 degrees centigrade. Next to that, we have to select that atmospheric pressure will be 1.01325 bar and temperature will be 20 degrees centigrade. Similarly, solid parameters also it will be 20 degrees centigrade. And also we have to select the coordinate system. In this case, we can see that fan will be providing cooling from top surface. That means the direction of fan will be Y. So we are considering the coordinate system as Y. Okay. Let us finish this. Now we can see that volume of fluid is being generated inside. It is done. Next to that, we have to hide that computational domain. Let us hide it. Next task will be to select the different fluid subdomains. We are considering air and water as two different fluids. Air will be inside this domain. So we can select the fluid subdomains from here. Insert fluid subdomain. It will be air and that will be inside this. So select other. You can select the face of extrude boss base 10 and that will be filled up with air. Done. Next to that, we have to select liquid for heat pipe. For better selection, you can cut the model as a segmented view from specific planes. Let us cut this one from right plane. In this way, we can have a better selection of the location, right? So insert fluid subdomain again. It will be water and that will be passing from this heat pipe. You can see this is the flow passage of water. Actually inside this heat pipe, very little amount of water will be there, and as it is being heated, it will be vaporized and it will pass throughout this space. Okay, done. Next to that, we have to provide some other properties like both the fluid subdomains defined. Next to that, we can provide material. Insert solid material. Predefined. It will be aluminum alloys, that means aluminum 6061, and we can provide aluminum alloys for the different parts, for the top part and the side parts. Select, and we can select the side parts also. Great, check. So aluminum is provided. Next to that, we have to provide different material. That is for copper, we have to provide insert solid material. Predefined, it will be metals and copper. Let us select copper from the geometry itself. You can select evaporator, adiabatic zone, and also condenser zone, and that will be considered as copper. Next to that, you can select that chip which is made up of silicon. You can select material, solid materials, insert solid material. It will be made up of silicon. So we can select material from here. It will be semiconductors, and let us select silicon for this chip. You can select chip from here itself. Select it. Go check. Materials have been defined. Another thing we can do, which is not necessary, actually the bottom surface should be made up of printed circuit board. Predefined, we can select the 2S2P1 as the bottom surface. Selected. Again check. Again, you have to provide aluminum for the fins. So what can you do is solid materials, insert solid material, predefined alloys. It will be aluminum 6061 alloys. Now let us select the aluminum fins. You can select it from here, from pattern, shift, and last one you can select. Selected. So we have provided aluminum to the fins. You can check it's done. We have to provide fan and also the properties of heat pipe to be given. And for providing these things, we have to select a segmented view of this model. We can cut it from different planes. Let us cut it from top plane. Select a specific view. We have cut it from top plane. Now we can select the specific locations for heat pipe properties. Conditions. Heat pipes. Initially you have to select all parts of the heat pipe. In the section 1, we can select the all parts of the heat pipe from the geometry. Evaporator is selected. Next one is adiabatic zone, and finally we are selecting that condenser zone. So all the heat pipe is selected. In the next section you have to select that heating zone. You can select the chip top surface as the heating surface. Last one will be the condenser zone. You can select condenser zone from the fins, or you can select one by one the fin surfaces. Let us select the fin surfaces one by one. All the fins are selected. Next one we have to provide the effective thermal resistance. This is a experimental property. It is depending on the temperature difference between the condenser zone and the evaporative zone divided by the input wattage. So its value will be in the range of 0.05. Done. Next we have to provide that fan. For providing the fan, we have to select again the specific section. We have to cut the model along specific section. Let us cut it from right plane and drag it to a specific location. This is the fan. Green check. You can rotate this one a little bit for selecting that fan location in a better way. Okay, done. Next we can input fan from here, conditions. Let us provide fan. It will be definitely one external inlet fan. Predefined, it will be axial flow fan. Let us select JMC products. We will select the highest one. Selected. For having the specifications of this fan, you can go through our previous videos where we have talked about PC cooling. Selected. Green check. This is the 12-volt fan. We can select the completed view of this model. This is the model. Rotate view. Done. And again, one thing is remaining. That means at the bottom surface we have provided some kind of rectangular slots that can be introduced from the SolidWorks interface itself. From here we can provide. So before providing that slots, we have to provide boundary conditions at this location as atmospheric pressure at the exit locations, right? So we can provide boundary conditions from here right now. Boundary conditions, insert boundary condition. It will be atmospheric pressure at the exit location. You can have a bottom view of this one. So this is the location. You can select the lead, select other, but to select the inside surface, that is face of lead 3. Selected. Green check. Done. Next to that, we have to provide rectangular slot from the SolidWorks interface itself. You can bring it from here, conditions. It will be perforated plates with a specific amount of perforation. For selecting this one, what we'll do is initially we'll make the top part hidden, then you can select this better way. The top part is hidden now. Now we can select this location in a better way, right? So we have to select that perforation from here. Conditions, perforated plates. Let us select that plate, and it will be predefined with rectangular slots with a specific amount of perforation selected. So from this one we will have exit of hot air. Okay, done. Now one thing is needed in our analysis. A heat source should be defined, and that heat source can be obtained from the conditions. It will be surface source, and let us provide a heating wattage to be 50 wattage from the surface of the chip. So it will be generating heat at a rate of 50 joules per second. Selected. Now to select that goals. Lot of goals to be selected. That means all will be in the form of surface goals. Goals. Insert surface goals. Initially you want to take the average temperature of fluid inside these copper tubes or heat pipes. It will be average temperature of fluid. You can select that regions. Select other. It will be face of sweep 6 selected. So this one is the evaporator section of the heat pipe. Selected. Again another goal to be selected. It will come from here. We have to have the average temperature of fluid inside the adiabatic section. So it will come from goals. Insert surface goals. It will be average temperature of fluid inside this adiabatic section. You have to select the locations. Select this one. Select other. Selected. First one. Select other. Selected. And the last part of this adiabatic section, select other. Selected. So this one we will consider as a single goal. We don't want to have separated goal for all this surface. This is actually consisting of the adiabatic section of the heat pipe. Selected. Then the last one, that means that condenser section of the heat pipe, we have to select. Again it will be selected from goals. Insert surface goals. It will be average temperature of fluid at the condenser fins. You can select the fins from the geometry itself. All the fins are being selected. Done. So we want to have a single goal for all these fins. That will be the temperature at the condenser zone. We can rename all these things. First one will be average temperature of fluid at evaporator. Second one will be average temperature of fluid at adiabatic zone. And the last one is the average temperature of fluid at condenser zone. Done. We want to have another thing, that means we want to have temperature at the exit location also to be selected as a surface goal. Goals. Insert surface goals. It will be average temperature of fluid at the exit location. Let us select that surface. Selected. Green check. And we can rename this one as average temperature of fluid at exit. Done. All the goals are defined. Next to that we can do meshing. We want to have better mesh to have better results. So global mesh, edit definition, and we'll go for manual one. Let us see the refinement level. Display refinement level. It is refined up to level 1. We can make it up to 3. for beta machine. Done. Ground check. It is meshed. Now we can go for simulation. We can run it. Let us run this one. Running with the new calculations. Let the iterations move on. You can see the solver window. Let us see the goal plots from the solver window itself. We'll select all the goals. Okay. Excluding the goal plots, we want to see the actual views. Let us see this one from right plane. Settings, we instead of pressure want to see temperature of fluid, and from image attributes we want to have a larger view of this one. You can see this is the location for heat pipe and also that chip. You can see both the things same side by side. You can see heat is being generated at the heat pipe, which is indicated by yellow color. That means temperature is very high at this location, and this is the region where air is there. So we are having different sections of the heat pipe. The initial section that is known as your evaporative section, that is having high temperature, which is indicated by 29 degrees centigrade, and temperature at the condenser zone little less, which is in the range of 25.44 degrees centigrade, and the atmospheric temperature is 20 degrees centigrade. Let the iterations move on. It is moving, and by the same time color of the heat pipe is also changing. You can see these things from different zones. Let us see another view. Let us select from front plane. Select the views from front plane, and settings will be temperature of fluid, and image attributes will be, let us select 1000 by 1000. This is from top, right? You can see different things. You can see views from two different planes. The top one is right view, the down one is front view, and bottom right side we can see the goal plots. As time is approaching, we are having different values. That means at the adiabatic zone temperature is 30.98 degrees centigrade. Adiabatic zone is having maximum temperature because it is exposed to the chip surface. So it will be having same temperature at the temperature of the chip. The solver is finished. You can see that convergence is achieved in all cases, and you can see from the goal plots that temperature at the adiabatic zone is 30.989 degrees centigrade. Temperature at the condenser zone is 28.193 degrees centigrade, and at the evaporator zone it is 32.70 degrees centigrade. So maximum temperature is obtained at the evaporator zone, which is exposed to the direct contact with the chip surface, and at the exit surface we can see the temperature is in the range of 23.873 degrees centigrade. Okay. Excluding that one, we could see some other goals like the temperature at the chip surface also we could see, right? Next to that, we'll see our results from the cut plots. Let us close these things. We want to see our results from different cut plots. Results, cut plots, insert cut plots. You want to see cut plots from different planes. Initially, we'll see the results from front plane. It will be temperature of fluid, grain check. It is better to see from front view only. And for seeing these things, better to make these things completely transparent. Okay, done. Now we can see the flow particles inside this one. First of all, we want to see the cut plots. Let us play the cut plots. Let us see from front plane. From the front plane, you can see how the heat is being transferred from the fins at the exit. and by the application of fan, it is being circulated downward direction. Let us clear and hide these things. Now we want to see these things in the form of animation from different plane. Let us see this cut plot from right plane. It is clearly understood that fan is forcing the air from top to down, and it is passing through the rectangular slot in the down position. And here you can see that heat is being generated from the chip and it is passing through the heat pipe. Let us try to see this thing from top plane also. Cut part 1, clear and hide. Now we'll try to see this one from top plane, and we'll cut this along this face, right? Cut part 1, edit definition, and we want to see from top plane, and we want to cut along a specific location, along the mid of the heat pipe. We'll check. So we have to see that model from top side also. Okay, so it will provide a better look. You can see in a better way how cooling is occurring inside. This is the complete view of the laptop cooling. Let us play these things. You can see the color in the heat pipe. It is initially red, and as it is approaching at the condenser zone, its temperature is little reducing. Let us clear and hide these things, and we want to make this one also transparent. Let us clear and hide. Cut plot 1, let us clear and hide, and we want to make this one transparent, make this one hidden. Now it will be easier to understand that flow particles inside this one, right? Now we can have a better view of this cut plot. Let us play this. For better cooling, instead of one pipe, we can use multiple numbers of heat pipes. In that way, cooling will be better. But here in this case, our main aim was to see how heat is being transferred from the chip to the exit location. Okay. Next, we are going to see dynamics of flow particles throughout this heat pipe, right? For seeing the dynamics of flow particles, you have to see the specific location. So better to cut this from specific plane. We'll cut this one from top plane. Let us cut this model from top plane. Let us cut this model from top plane, right? And you can drag it as per our requirement. Green check, done. Now you can select the specific location better way. Flow trajectories, insert. Instead of 20 numbers, we'll make this one 100 numbers. 100 numbers of flow particles in the form of arrows. And let us make the size of these arrows a little bit bigger. It is 0.203 meter. Let us select the surfaces from which these flow particles will be moving. And we can select the exit surface also. Selected. Green check. Now we can see the complete view of the model, and this is the dynamic of flow particles. You can see. Let us play these things in the form of an animation. Flow trajectories, let us play. You can see the circulation of these flow particles. That is because of this fan. Again, you can see at the bottom side also, fan is forcing out those hot air particles. That is indicated by the color, yellow color. So hot air particles are moving out from the bottom surface. That is done by using the fan, right? And also some particles are going inside this zone, which is forced out by the fan, right? If we see from top view, it will be clear to see. Now heat flow, we can see the temperature of air, it is in the blue zone. That means by using the fan, the temperature of those hot particles are being reduced. And the particles which is moving downwards, we can see the color of this one is yellow and green. Those particles are having high temperature, and those are forced out from the downward position where rectangular slots are provided. Okay. The blue color air particles are emanating out from the fins, and that is why being circulated by the movement of the fan. Let us see this one from front view. Let us clear and hide. Next one, we will see the goal plots. Insert goal plots, and we will see all the results in the form of graphs. Let us select all these things. Let us show. These are the results which one we have already seen from the solver window itself. Now I want to see all these things in the form of graphs from history. These are the results. First one is the average temperature of fluid at the evaporator end. Initial temperature was 20 degrees centigrade, and after 78 numbers of iterations, we got the final temperature of evaporator end is 32.7 degrees centigrade. Similarly, for the second one, you can see the adiabatic zone. Initial temperature was 20 degrees centigrade, and after 78 numbers of iterations, we got the final temperature at the adiabatic zone as 30.98 degrees centigrade. Next to that, you can see the condenser zone, which was surrounded with fins made up of aluminium. Again, you can see at the end of 78 numbers of iterations, average temperature at the fins equal to 28.19 degrees centigrade, and finally you can see the temperature at the exit is in the range of 23.85 degrees centigrade. Okay, so we could see that at the exit temperature is very less, it is 23.85 degrees centigrade. Next to that, we will go for some kind of parametric study and we'll change the input wattage of the heater and see what are the different values of exhaust temperature and also the temperature at the different surfaces of heat pipe. Okay, we have undergone already one parametric study of this analysis with the input wattage of 100 to 500 wattage. Let us see the results from the goals. You could see that here when the wattage of the heater was 100, you could see that temperature at the exit surface was 43.43 degrees centigrade, and when the wattage is 200, exit temperature at the outlet is 67.18 degrees centigrade. When the wattage is 300, the output temperature at the exit location is 90.82 degrees centigrade, and when the wattage is 400, you could see that temperature at the exit location is 115.2 degrees centigrade, and finally when the wattage is 500, the final temperature at the exit location is 139.81 degrees centigrade. Together with that, we have seen some other results, that temperature at the adiabatic zone, initially with the wattage of 100, it was 22, right? So you can see all the results here. Here we have included one thing, that is average temperature at the processor also included. So you can see almost it is same temperature at the processor and also at the evaporator, right? So it was having direct contact with the processor, so its temperature is almost same compared to the processor. And again you can see average temperature at the condenser, where the fins are provided, it is also having almost similar temperature. It is in the range of 36, right? This is all about our video regarding heating management or thermal management of a laptop using heat pipe. In our next video, we will go for some kind of performance analysis of a heat pipe with a normal copper pipe. Okay, thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.